Okay, so we're going to go ahead and go over our next lesson from section 1-3 on transformations of functions. So before we get started doing that, I want you guys to sketch the graphs of these six functions down below. So I want a really quick sketch of the graph. I don't want you plotting points. Like I want you to knock these sketches out in like 2 seconds apiece. Okay, so go ahead and pause the video while you do that, and then whenever you're done, go ahead and unpause, and we will take a look at these graphs. Okay, so when we take a look at the graph of the function f of x is equal to x squared, that's a parabola whose vertex is located at the origin and opening up. The graph of f of x, which is equal to x cubed, is going to look like so, okay, where the graph lies in quadrants 1 and 3. The function f of x equal to the absolute value of x, as we saw in the previous lesson, is a v-shaped graph whose corner is located at the origin. The function f of x equal to rad x is going to start at the origin and extend up and to the right. The function f of x equal to the cube root of x, that graph is going to lie in quadrants 1 and 3, like this. And then when we look at the function f of x equal to 1 over x, that graph also lies in quadrants 1 and 3, looking like so. Okay, so when it comes to us using transformations to graph functions, these are going to be the six functions that we are going to shift around in the coordinate plane in order to look at their graphs. Okay, so what we're going to do next is we're going to take a look at our rules for transformations of functions. Okay, so for these rules, we're going to let a be greater than 0 and c be bigger than 1. And then when we have our function y is equal to f of x over here, um, points on that function are going to look like this. They're going to be of the form x comma y. So not only are we going to look at like what the following transformations do to the function itself, but what they're going to do to every single point on the graph of said function. Okay, so when we look at our first transformation, if we have y is equal to f of x minus a, okay, so if we subtract a inside of the function, that is going to shift our graph to the right a units. So if we shift our graph to the right a units, this point over here, sorry, this point over here, x comma y, if we shift the graph to the right a units, only the x coordinate is going to get affected. So our corresponding point, if we move our graph a units to the right, is going to be the ordered pair x plus a comma y. Okay, if we take the function y is equal to f of x plus a, where we add a inside of our function, that's going to shift our graph a units to the left, which again is going to affect the x coordinate only. So the new x coordinate of our point will be x minus a, and the y coordinate stays the same. Okay, so if we add a outside of our function, so if we take the function y is equal to f of x plus a, that is going to shift our graph up a units. Okay, so if we move up a units, only the y coordinate of our point is affected. So our new point is going to have coordinates x and then y plus a. If we take the function y is equal to f of x minus a, that's going to shift our graph down a units. Again, only the y coordinate gets affected, so our new point is going to have coordinates x and then y minus a. Okay, next transformation is if we take the function y is equal to f of negative x. So if we take the opposite of the input only, that is going to correspond to a y-axis reflection. And if we reflect our point x comma y across the y-axis, we do that by taking the opposite of the x coordinate. So that is going to correspond to the ordered pair negative x comma y. For the next one, if we take y is equal to the opposite of f of x, that's going to be an x-axis reflection. When we reflect a graph across the x-axis, that results in us taking the opposite of our y coordinate. So our new point is going to be the ordered pair x comma negative y. Okay, if we multiply out front of our function, so if we take y is equal to, if we multiply out front of our function by c, where c is a number that's larger than 1, that's going to correspond to a vertical stretch by a factor of c. Okay, so when we vertically stretch, the y coordinate gets affected. Our new ordered pair is going to be the ordered pair x comma c times y. Okay, when we multiply out front by 1 over c, that's going to correspond to a vertical compression by a factor of c, once again affecting the y coordinate only. And then we're going to take that y coordinate and multiply by the coefficient up front. So y times 1 over c is y over c. Okay, so I want to go really quickly back to two of the functions that we've looked at. Okay, so the function f of x equal to x squared and the function f of x equal to the square root of x. And I want to take a look really quickly at what happens when we vertically stretch or vertically compress a graph. So when we vertically stretch a graph, you want to think about taking the graph and pulling it vertically. We're going to pull it up and pull it down. So if I were to vertically stretch the graph of x squared, I'm going to do this in red so it shows up a little bit better. When I vertically stretch the graph of x squared, multiplying by a number that's bigger than 1, that's going to wind up like making that graph grow faster in the y direction, which winds up narrowing the graph of x squared. If we vertically stretch the graph of rad x, again, that's going to pull that graph vertically. It's going to make that graph open up bigger or open up wider. Okay, so it's again, that's the same vertical stretch for both of those functions, but how it affects the graph of both of those functions is a little bit different. Okay, now if we compare that to a vertical compression, when you vertically compress a graph, you want to think about like what I'm drawing in green here, or smashing that graph or pressing that graph against the x-axis. So if we look at the function f of x equal to x squared and we vertically compress that graph, that's going to make the graph not grow as fast or widen the graph of that function x squared. If we do the same thing with the function f of x equal to rad x, if I press that graph against the x-axis, that's going to make that graph not open as wide. Okay, so it's going to wind up like narrowing that graph vertically. Okay, so I want to make sure that you guys are clear with how vertical stretches and compressions affect the graphs of those functions, because we're going to take a look at some examples of graphing those functions momentarily. Okay, I think the trickiest transformations are the last two, where if we have y is equal to f of c times x, that is going to result in a horizontal compression by a factor of c, okay, which is going to affect the x coordinate of our point only. And what we do when we horizontally compress is we take the x coordinate of our point, and then we're going to multiply it by the reciprocal of the coefficient of x. So the coefficient of x is c. If I multiply x times the reciprocal of that. That gives me 1 over c times x, which I can rewrite as x over c. And then if we have the function y is equal to f of 1 over c times x, that is going to correspond to a horizontal stretch by a factor of c. So again, the x coordinate is the only one that is affected. We're going to multiply that x coordinate by the reciprocal of our coefficient. So the reciprocal of 1 over c is c. So that's going to make the coordinate of our point cx. Okay, now, as I mentioned, like, you guys should be very familiar with the first set of transformations. The only ones that may be new to you are these two right here. And I'm going to give you what I use to help me remember, like, which transformations are which. Okay, so to help me keep track of transformations, the way I like thinking about this is when we perform an operation inside of the function, the graph is going to behave the opposite of what you would expect. Okay, so if you subtract a inside of the function, you would probably think that the graph would get shifted to the left a units, but no, the graph behaves the opposite of what you would expect. That's going to shift the graph to the right a units instead. If you take y is equal to f of x plus a, if you add a inside of the function, you would probably at first glance think, oh, that's going to shift the graph to the right a units, but no, graph behaves the opposite of what you would expect. The graph gets shifted to the left a units. And same thing with these last two. Multiplying inside of our function by c, you would think, oh, that graph is going to get horizontally stretched by a factor of c, but no, graph behaves the opposite of what you would expect, so the graph gets compressed by a factor of c. And then for 1 over c times x, you would think that multiplying out front of the function by 1 over c would horizontally compress that graph, but no, the graph behaves the opposite of what you would expect, so the graph gets stretched. Okay, what you do outside of the function, the graph behaves the way you would anticipate. So for this one, if we take f of x plus a, you would expect that graph to get shifted up a units, which it in fact does. F of x minus a, you would expect that to get shifted down a units, which it does. C times f of x, you would expect that graph to get vertically stretched by a factor of c, which it does. 1 over c times f of x, you would expect that to get vertically compressed by a factor of c, which it does. Okay, so again, operations inside of the function behave the opposite of what you would expect. Operations outside of the function behave how you would expect them to. Okay, so the way I teach graphing using transformations, as a math teacher, you don't have to do things in this particular order. But I found as a teacher, if you do things in this particular order, you will wind up graphing using transformations much more correctly and efficiently. Okay, so there is a specific order that I want you to utilize when graphing using transformations in my class. Okay, first step always is if your function has a horizontal shift, you must perform that horizontal shift first. Okay, so horizontal shift is step number 1. And the step that we perform last, if our graph has a vertical shift, we vertically shift that graph last. Okay, steps 2 and 3, where we reflect or stretch or compress, does not matter which order you do steps 2 and 3 in. Okay, me personally, when I work these out, I like stretching horizontally first, shifting horizontally first, shifting vertically last, and then whether I stretch or compress or reflect is dependent on what I am doing from inside of my function out. Okay, so let's take a look at um, some examples, graphing using transformations. Okay, now I'm not going to like start with easy examples and build into more difficult ones. I'm just going to start with like as challenging as I can make these questions right off the bat. So these examples that we do to close this lesson out, these would be like examples that you can see on your quiz next week or on your test whenever you take your first midterm. Okay, so directions here say to sketch the following functions. For number one, we have y is equal to -2 times the quantity 2 minus x cubed plus 4. Okay, so when I work these out using transformations, I'm going to work the graph out one step at a time. Okay, I don't want to make careless errors, but I can still work through this very efficiently. Okay, so to start out with here, I'm going to start with my base function. My base function is x cubed. Okay, so graphically, the function of x cubed is going to look like so. Okay, now we're going to use the order that I talked about just prior. Okay, so what I want to do is I want to take this function x cubed and I want to transform it step by step until I get that function highlighted above. Okay, so I want to perform my transformations in order to make that happen. Okay, so first transformation for me, if I want to transform x cubed into that highlighted function, is there a horizontal shift that I have to perform? And the answer is yes. Okay, so I'm going to do that horizontal shift first. Okay, so I'm going to take the function 2 plus x quantity cubed, or x plus 2 quantity cubed, and graph that next. So if we add 2 inside of our function, that's going to shift the graph 2 units to the left. Okay, so graphically our function looks like so. Okay, I know I'm going to do the vertical shift last, so that plus 4 I'm going to save for my final step. So I'm going to continue transforming the function on bottom into the highlighted function one step at a time from the inside out. Okay, so the next function we are going to graph is 2 minus x cubed. So I'm going to take the entire graph from the previous part and I'm going to reflect it across the y-axis. Okay, so that's going to move my graph over here to 2, 0. And then when I reflect the previous graph across the y-axis, the graph is going to look like so. Again, continuing to work from inside of my function out, the next function I'm going to graph is 2 times 2 minus x cubed. Okay, so when I multiply out front of my function by 2, that's going to involve me vertically stretching my graph. Okay, so when I vertically stretch my graph, it had better be clear that you vertically stretch your graph. You had better draw that graph more narrow than what you did in the previous part. Okay, so it's pretty clear that that function there is more narrow than what we drew in the previous part. So that is an effective vertical stretch. Okay, again, continuing to work from inside out. Next function I'm going to graph is -2 times 2 minus x quantity cubed. So when I take the opposite of the entire function, that's going to take the previous graph and reflect it across the x-axis. So when I reflect across the x-axis, my graph is going to look like so. And then my last step is for me to add 4, which is going to take the previous graph and shift it up 4 units. So this is where I'm going to draw like a neat graph. I'm going to label my dash marks in each direction, so that's going to be 1 unit. This will be 1 unit in the y direction, and then that's my starting value, and then we're going to go ahead and just graph our base function like so. Okay, so this right here is the graph of that function using transformations. Again, we're not plotting points, okay? Like the graph doesn't have to be like perfectly detailed. I'm looking for like the correct starting function, your graph having the correct shape, opening the right direction, and then yeah, having the correct starting point. Okay, so I'm going to give you guys this one to work on your own. Okay, so go ahead and pause the video and work this one out. When you're done, you can unpause and check your final graph. Okay, so let's see how we did with number 2. So for number 2, our base function is radx, whose graph will look like so. Again, if there is a horizontal shift to be performed, we're going to do that first, and in this case there is. So the next function I'm going to graph is radx minus 3. Or you can do like negative 3 plus radx. They're both the same thing. Okay, so that's just going to take this graph and shift it 3 units to the right. Okay, so our graph looks like so. Next, working from inside of my function out, next thing I'm going to do is I'm going to take the opposite of the x value. So this is negative x minus 3. So when I take the opposite of the x value, I'm going to take my previous graph and reflect it across the y-axis. Okay, so when I do so, the graph is now going to start at negative 3, 0 and open up and to the left. I'm going to multiply that function out front by 1/2. So when I multiply out front by 1/2, that is going to vertically compress my graph. So I'm going to draw my graph not opening as big as the previous example. Okay, so I'm going to draw the graph not opening as large, like so. I then am going to take the opposite of my entire function. So when I take the opposite of the entire function, the graph is going to get reflected across the x-axis, looking like so. And then for my final function, we have y is equal to negative 1/2 rad negative 3 minus x plus 2. So adding 2 to our function is just going to shift our graph up 2 units. Okay, so our starting point is going to be over here at negative 3, 2. And then our graph is going to open down and to the left like so. Okay, so that right there is the graph of our final function. Okay, and again, like this is as complicated as I can make one of these problems. Okay, so as long as you guys follow the order listed above here, you should be in good shape when it comes to graphing using transformations. Okay, I'm going to do something a little bit different for the last set of examples. So directions here say given the function y is equal to f of x contains the point 1, 5. Find the corresponding points on the graph of the given function. Okay, so I want you, when working this example out, I want you to see where the point 1, 5 gets moved on the graph of this function here, which is y is equal to negative 1/3 f of x plus 3 minus 2. Okay, so pause the video, try to give this one a try. When you're done, unpause and we'll check and see how you did. Okay, so maybe you were able to work this through fine. Maybe you had difficulty working this through because we haven't really done something like this yet. But this reflects the same content that we talked about earlier. We're just, instead of looking at how transformations affect the actual graph of a function, we're going to take a look at how transformations affect points on the graph of a function. Okay, so we're going to perform our transformations in the same order that we did up above. So if there is a horizontal shift to be performed, we're going to go ahead and do that first, which there is here. So first function we want to look at is y is equal to f of x plus 3. So if we add 3 inside of the function, the x coordinate gets affected. We shift the graph 3 units to the left. So if I shift the point 1, 5, 3 units to the left, it is now at negative 2, 5. Okay, I know I'm vertically shifting last, so I'm going to work inside out for my next transformation. So I'm going to multiply 1/3 times f of x plus 3. We know that that corresponds to a vertical compression. When we vertically compress, the y coordinate gets affected, and we're going to multiply the y coordinate of our point by that number 1/3. So 5 times 1/3 is 5/3. Okay, again, working one transformation at a time. Next thing I'm going to do is take the opposite of that entire function. When we take the opposite of the entire function, that is going to be an x-axis reflection. When we x-axis reflect, we take the opposite of the y-coordinate. So our new point is now at negative 2, negative 5/3. And the last thing I'm going to do is subtract 2, which shifts the graph down 2 units. So if we shift down 2 units, the y-coordinate gets affected. So we're just going to take our y-coordinate and subtract 2 from it. And negative 5/3 minus 2 is going to be negative 5/3 minus 6/3, which is negative 11/3. Okay, and that is the location of that corresponding point on the graph of the highlighted function. Okay, so I want you guys to give these next 2 examples a try. You can go ahead and pause the video now to work them out, and then when you're done, you can check your work. All right, so let's check and see how we did here. Again, with both of these functions, we're going to start with the 0.15 on the graph of y is equal to f of x. Now, when I look at number 2, there is no horizontal shift to be performed here. So I'm just going to work from inside of the function out and then do the vertical shift last. Okay, so I'm going to start by taking f of 3x. So when I take f of 3x, I know that that is going to be a horizontal compression, which affects the x coordinate of our point. We're going to multiply the x coordinate of our point 1 by the reciprocal of that coefficient, which is 1/3, and 1/3 times 1 gives me 1/3. The y coordinate remains 5. Okay, next I'm going to take the opposite of that input value. So when I take the opposite of the input value, that corresponds to a y-axis reflection. Y-axis reflection means I'm taking the opposite of the x coordinate. I next am going to multiply out front by 2. So when I multiply out front by 2, that is going to correspond to a vertical stretch. So I'm going to take the y coordinate and multiply it by 2, which gives me the ordered pair negative 1/3, 10. And then the last thing I'm going to do is I'm going to take that function and add 1, which shifts the graph up 1 unit, which affects the y coordinate. I'm going to add 1 to the y coordinate. So that's the ordered pair negative 1/3, 11. All right, I'm going to do the same thing with 3. So I'm going to do things a little bit differently here. In this example, when I work it out, I'm just going to work through all the transformations in order, and then we're going to find the corresponding points for all of the transformations at the end. Okay, so is there a horizontal shift to be performed? Yes, there is. So the next function we want to look at here is f of x plus 4. Then I'm going to work from inside of my function out. So next I'm going to take the opposite of the x value. So that's negative x plus 4, which is the same thing as 4 minus x. Next step is for me to multiply out front by 1/4, which is going to be a vertical compression. Last step is to subtract 3. Okay, so if we shift the graph to the left 4 units, our point is going to be at negative 3, 5. Our next step is if we take a y-axis reflection, we're going to take the opposite of the x coordinate. So that is now at 3, 5. When I multiply out front by 1/4 and vertically compress, we're going to take the y coordinate and multiply it by 1/4, which is 5/4. And then the last thing, subtracting 3, shifts the graph down 3 units. So when I subtract 3 from 5/4, that's the ordered pair 3, negative 7/4. Okay, so those are your corresponding points on the graphs of those two functions, respectively. Okay, so that's it. Once you guys have completed this video, you guys have the rest of the period in class to work on your homework assignment. If you're done with the homework assignment from section 1-2, just work on 1-3. Otherwise, you have your choice to work on the homework from section 1-2 or 1-3. Okay, so don't forget quiz on Wednesday, which is going to cover sections 1-1, 1-2, and 1-3. Hope you guys have a great weekend, and we'll see you all on Monday.